Alright, hello everybody, and today we're going to be deriving the complex exponential definition of the cosine and the sine using Euler's formula right here. So we want to redefine cosine of theta as well as the sine right here as some kind of combination of exponentials here, and here's how we're going to do it. Let's plug a negative into this argument right here. So we're going to end up with e to the negative I theta being equal to, so now we have a negative theta instead. So if we have a negative theta right here, we need to have a cosine of negative theta right here. But cosine is an even function, so plugging in a negative won't change anything. So cosine of theta still stays the same. And now we have I sine of theta. Sine is an odd function, so if you plug negative theta into here, we're going to get negative sine of theta. So by that, we're going to get negative I sine of theta. So now, how is this useful right here? Notice that we still have our cosines right here, as well as I sine theta on both equations. And the cool thing is, these I sine of thetas right here have different signs. So what that means is if we add these two equations together, we're going to get e to I theta plus e to the negative I theta, and cosine plus cosine is 2 cosine theta, and the positive and the negative will cancel each other out. So these two will disappear, and you see, now we pretty much got cosine on its own without this sine right here. So all we have to do is divide everything by 2, like so. And there you go, we have the complex exponential definition for the cosine. So how about for the sine? Well, we still need these two formulas right here, but instead of adding this time, what we're going to do is subtract. And why do we subtract? Well, we want to get rid of these cosines right here, because cosine minus cosine is exactly 0. And if we have I sine theta right here, minus a negative I sine theta, we're going to get 2 I sine theta. So what are we going to get if we do this right here? We're going to get e to the I theta minus e to the negative I theta being equal to cosine minus cosine is exactly 0, and we have this part double negative, so it turns into a plus. We're going to get 2i sine of theta, and just like before, we've gotten rid of these cosines right here, so we've got this sine right here, and all we need to do now is isolate this sine by dividing everything by 2i like so. So now we also have the complex exponential definition of the sine being e to the I theta minus e to the minus I theta over 2i. So that's pretty cool. And the nice thing about these complex exponential definitions is that theta can be any complex number. So why not replace thetas with z's right here, just to make it clear that we can have any complex number in the argument. And using these definitions right here, we're actually not restricted to the input of our sine and cosine being real numbers. We can extend it to complex numbers as well. So we could actually define things like sine of I. Well, sine of I, we can just use the complex exponential definition of the sine. And if we plug I into these z's right here, what are we going to get? Well, we're going to get e to the I times I, so replacing z's with i's right here, then minus e to the negative I times I, and then we have over 2i. And just combining these i's up here, we're going to get e to the negative 1 minus e. I times I is exactly negative 1, but we have this negative right here, so we have e to the first power over 2i. And you can leave your answer like this, or you can go further and say that, well, this is exactly 1 over I times e to the negative 1 minus e to the 1 over 2. And the reason why I split it up like this is because this almost looks like the hyperbolic sine. But the problem is these two e's here kind of need to be switched. So if we factor out a negative right here, we can switch these two e's around. So this will have e to the first power and e to the minus 1. And just moving I up to the top here, if we multiply the bottom by I, multiply the top by I, we're going to get negative 1 down here and an I up here. Negative 1 and negative 1 here will cancel, and we'll just get I in the end. And this is exactly the hyperbolic sine of 1 right here. So in the end, sine of I is exactly I times the hyperbolic sine of 1. So that's pretty cool. So pretty much using these complex exponential definitions right here, you can extend the domain of our inputs here to the whole complex domain. And of course, you can derive other trig exponential definitions as well using these two right here. But yep, that's pretty much it. So hope you guys enjoyed it, and I'll see everyone next time.